Alrighty guys, hello. I'm Dylan Vish, your SI leader for this class, Chem 202 with Dr. Kuda. And here I'm just going to go over this Chapter 54 quiz, which is our first quiz on acids and bases. I'm going to try this out. This is the first time I've done a video like this, so please let me know what you think about this. I'm going to leave a link to a survey at the end of this, so if you stopped already and said, hey, this is terrible quality, please fill out that survey and let me know. And I'll remind you at the end too. So, let's go ahead and try this quiz. So, our quiz on acids and bases, we have two main things going on. We have acids and we have bases. So the first question on this quiz is, what are the 6 strong acids? What are strong bases? Well, we should automatically think of our 6 strong acids as our halogen acids, meaning we have HCl, HBr, and HI. And the interesting thing about those three is that they're in the 7th group on the periodic table. If I just draw this little nice sketch of the periodic table over here, you know, you can kind of see the periodic table going on there, kind of interesting. We have our group 7 right here. We have fluorine, chlorine, bromine, iodine, and then we have some other ones below it. But notice that these 3 are all strong acids. So it's interesting to note that fluorine, or the fluorine acid, or HF, hydrofluoric acid, is not a strong acid. And we know that because this guy right here, he has H bonding, which kind of lowers that amount of acid effect you get going on there. But that's only 3 of the 6, so what are the other? Those are the harder ones to remember. So first one that we probably all recognize is sulfuric acid, H2SO4. What Johnny thought, you know, have you ever heard that little riddle? Johnny was a chemist's son, but Johnny is no more. What Johnny thought was H2O was H2SO4. Very interesting, right? Maybe you'll remember that. So, anyway, the next one is nitric acid. We might remember this one pretty well. HNO3. Strong acid as well. Now, this is the hardest one in my opinion. This is perchloric acid, HClO4. Now, watch out with that little 4 in the end there, because sometimes you'll see a 3 or a 2 or even a 1 or nothing there, an implied 1. And those are not the strong. It's got to be the 4 right there is the strong acid. So those are our 6 strong acids. And so strong bases. Well, we don't really say, oh, these are the strong bases. We just have a kind of generalized idea. Typically we have group 1 and 2 hydroxide salts. And this is something like KOH, NaOH, like in our labs we've seen. And we also have group 1 and group 2 oxides. This one we don't see as much though. We mainly see these OH minus salts, these hydroxide salts. Alright, so what is the autoionization of water? Going on to number 2 here. Autoionization is kind of what it sounds like. We see this word auto, and if you're a biology person, you've seen this a lot. But even not, like an autobiography. This is a self biography, a biography by yourself, or in this case is self-ionization. We know what ionize means. It means go from something into its ions. Well, if it's autoionization of water, we have water becoming ions. There we go, and this is a reversible reaction, so I'm going to draw my 2 arrows there. And so this thing has a nice specific constant we call Kw, which is our H plus times our OH minus. And at 25 degrees C, we know that Kw value as, wait for it, 10 to the minus 14. That's a good number to remember, your Kw value there. So don't forget that. Now, next question, number 3, we're looking at label the conjugate pairs of each of the following acid-base reactions. So let's look at the first one. Obviously, this guy, HF, is our acid. We have H2O as a liquid, okay. Let's look on the other side. We have H3O and HF minus. We can see immediately that these two are connected because they both have the weird atom, as I like to say, of the fluorine. So therefore, F must be the conjugate. In this case, we call that the conjugate base, but we're going to go further into that later. But that is the conjugate. And therefore, that would lead to imply that these guys are conjugates as well. And that makes this guy the base, and this guy the conjugate acid. But again, we'll go into the conjugate acid base a little bit further A little bit later, I mean to say. So in this next case right here, C2H4, yeah, it doesn't look like a typical acid or base that we've seen, but for the sake of this problem, let's imagine it is. So in this NH2 and this NH3, we can automatically see that they're paired because, again, that nitrogen, that weird atom, is the same there. And so that kind of puts us to say that these guys must also be the same. But can we identify which ones are the acids and bases? Well, NH2 gains a proton, so therefore this must be a base. And therefore it's the conjugate acid of this one. And so that must mean this guy is the acid. Right there. And this guy is a base. And I believe, yeah, cool. It's a conjugate base. Moving on, again, we can kind of see that these ions are related, and this H and H plus and this are related. And so we can again see what's going on. Well, this guy is producing H plus. So again, this is a weirder type situation. But again, we have our, let's see, since we're producing H plus, this is obviously an acid reaction. This guy's acting as an acid, this guy's acting as a base. So, cool. So let's write the K expression for each of the above reactions. So the first one, we have products over reactants, right? It's going to be F minus H3O plus all over our HF concentrations. Now remember, H2O is a liquid, so we do not include it. The second one, we have again NH3, C2H3 all over NH2, and C2H4. Let's go ahead and say that. Now I know we didn't have phases. I should have included phases in that one right there. But so I'm assuming that they are all aqueous phase elements, or compounds, I mean to say. So our final K value here, we have K is equal to products H plus, and that's cubed because we have that coefficient of 3. FeOH taken 3 times all over Fe3 plus. Now again, H2O is not included because it is a liquid. Alright, so let's start working on this number 5, the math problem here. Might be a little difficult. So we have this nice little equation here. And they give us this K value right here. So we will see what we can do with this. Well, the first question seems simple enough. Is this an acid-base reaction? Well, what's produced? We have H3O plus. For producing H3O plus, that's an acid. What is a base? A base is when you produce OH minus, or you can say or remove H plus. That's also a way. And an acid produces H plus or removes OH minus in a similar fashion. That's 2 straightforward ways to denote an acid or a base. So what's the conjugate acid and what's the conjugate base? Well, let's see. What are the conjugate pairs? We kind of denoted this earlier. We can see that these two are very closely related, and these two are. See, H2O, H3O plus, they differ only by an H. H2C2O4, HC2O4 minus, they differ only by an H. That's what we defined as conjugate pair. And so we can see that the left one has one more H than the right one. So this is the acid, this is the conjugate base. And that must mean this guy must be a base. This is the conjugate acid. Okay, sound good? Great, moving on. And so that's B right there. Now C, the actual math here. What's the pH at equilibrium given the initial conditions, concentrations? So this is just like a problem we've done before. They give us an equilibrium problem, and they're saying, okay, they give us an equilibrium equation. They said, here's what we started with. These are our initial concentrations. What's at equilibrium? And the only difference is they're asking pH, and pH equals negative log of our H plus concentration. So we just need to find an equilibrium concentration of H plus or H3O plus, because remember they're the same thing. And then we'll be able to calculate the pH. So what we need to do is we need to make an ice table. Initially, we have we have our HA plus our water in equilibrium with our A minus plus our H plus. HA, we have 0.0243. H2O we don't care about because it's a liquid. A minus. We got 0.0130 and 0.0034. Now, which direction does this go? Now, to be honest, it doesn't really matter. We could do it the wrong way. We could do it the right way. We could just guess. But there is a way to check. We can check our Q value. So let's go ahead and write our Q expression. We have our H3O times our HC2O4 all over our H2C2O4. We can plug the values in we were given in the equation. 0.0034 for our H3O plus, and H2C2O4, that's 0.0130 divided by 0.0243. We'll plug that into our calculator. Sorry, I forgot to plug this one in. 0.018, which is 1.8 times 10 to the negative. Oh, sorry, it's a 0 there. 3, which is definitely greater than K. Since Q is greater than K, that means we have too much products, because products are reactants. This is what Q and K are, essentially. So we have too much products, therefore, we're going to go left. So we're going to minus X here, minus X, and plus X. And so these are all of our equilibrium amounts. Cool? Great. And so now we can use this in our K expression. Minus X, I forgot that there. Now sadly, this K value is pretty large. It's 1.4 times 10 to the negative fourth. Now we could use the approximation I've showed in the SI sessions before with our calculator using the answer symbol, but in this case I'm just going to use our quadratic formula. It's a little bit weird because there's a lot of pluses and x's and minus x's, and it would be hard to decide which x you couldn't get rid of if you were to do an approximation method. But if you wanted to, it's most likely going to be this one that you could keep. Everyone else you could approximate as 0. No, my mistake. I was backwards there. This one is the one you want to keep. And then everyone else you could say, oh, that's about 0, and then go from there. I decided that because notice 0.0034, it's the one with it's the smallest number up there. So it's going to be it's going to be the one that's most affected. So using our nice mathematical prowess, we can actually manipulate this equation. This is multiply this guy over here, multiply these two together, and you'll end up with an equation such as this: 4.0798 times 10 to the negative 4th, 0.01654 plus x squared equals 0. That's a decent amount of math there, so if you have any trouble with that, let me know, and then we can talk about it individually. But otherwise, now we can plug this into our quadratic formula, which is negative b plus or minus the square root of b squared minus 4ac all over 2a. And so we can do that. And obviously this equation should be provided to you on the test, so don't worry about that if you don't know it. But it's a good thing to know. And so we'll get two answers here, as always with the quadratic formula. 0.00302. Now one of them will be physically possible and one will not be typically. Now since both of them are positive, at least that's good. But we can notice that if we plug this one in to this number right here, let me try that again with a different color. So we plug that one in to this guy right here, that's going to give a negative number, and we can't have negative concentrations. So therefore, that is a bad number, and we're going to use this one right here. And so, if our x is that's not our answer to the question, because the answer question is what's the pH. And then to get that, we need the concentration of H plus. Concentration of H plus 0.0034. 0.0034 minus our x, 0.00302. That's going to give us 0.00038. So the negative log of 3.8 times 10 to the negative 4, that's going to give you 3.42. That's our pH at equilibrium. Now this question D, given that I gave you initial concentrations that were not 0 on the right hand side, this question is actually invalid for this case, because typically what you would do is you would say the amount of your A minus all over the amount of your HA, which would be the concentration of C2O4 minus now typically this is only talked about when you have nothing on the right side, but we can still kind of use this equation to put this forward. And so our equilibrium amounts, that's important. These are equilibrium amounts. That's going to be 0.0130 minus our x all over whatever, again, 0.0243 plus our 0.00302. We'll plug that into our calculator. And you'll get about 0.36. Multiply that by 100, you'll get 36.5%. That's actually pretty high. Pretty. Yeah. So yeah, pretty good. Awesome. This is a good enough answer for now. So what does it mean if a compound is amphoteric? Well, we've seen this word amph before in many different cases. Amph essentially means both. And in this case, we're talking about both, meaning both acid and a base. So amphoteric means it's both an acid and a base. A typical example is water. Because again, if we put water with an acid, the water will act as a base and take off that proton. But if we put it with a base, water will then donate a proton. OH minus. Then it'll act as a base. And notice again with that, where'd it go? With that original idea of H3O plus producers are acids, OH minus producers are bases. So that's the quiz chapter 54. Let me know how this video worked for you all. I know it was a little longer than I expected, so if that's a problem, let me know. Give me feedback on what you think you'd like in the future in videos like this, or anything along those lines. I hope you had a great spring break, and I look forward to seeing you soon. Have a great day. Bye.